In our today's class, we will try to learn about principle of capacitor. After this principle of capacitor, we will try to learn about parallel plate capacitor with no medium in between the parallel plates, and lastly we will try to learn the parallel plate capacitor with some dielectric medium in between the parallel plates. Okay, so first let's try to learn about this principle of capacitor. Now if you keep an insulated conductor which is charged with a positive, okay, then on the conductor, on its surface, positive charges will be there. And then what happen if you bring an uncharged, okay, conductor then near to the charged conductor, then what happen near to the surface of this charged conductor, the uncharged conductor will develop what? Opposite charge. If it is positive charge there and near to it, if uncharged conductor is brought, then what happen near to the surface of the charged conductor, opposite charges will be developed. If this is positive charge, then opposite means negative charge will develop near to the surface of the conductor, and onto the farther side of the conductor, what happen? Positive charge will be developed. That means similar charge will be developed. Got it? So due to this, what happened? The potential decreases. Why? Because if it had been positive also, then what happened? Potential of this charge conductor would have been increased. But due to this negative charge, what happened? Due to this negative charges developed near to the surface of this charge conductor, the potential of this charge conductor decreases. Now what happened if you try to connect this uncharged conductor to the earth? That means if you added this uncharged conductor that is brought near to the charged conductor, then what happened? All these positive charges will go down to the earth. Okay, this positive charge will go down to the earth, and what happened? There will not be no positive charges. This further reduces the potential, okay, the potential of this charge conductor, and so what happened? The capacitance of this system or arrangement will be greatly increased. Why? Because we know that capacitance C is equal to Q by V, right? So if your V decreases, then naturally what happen? This whole ratio, the whole ratio will be what? Increase. Yes, we know that your C is equal to what? Q by V, right? Q by V. If your potential decreases, then what happens? The whole ratio increases. The whole ratio means what? Capacitance increases. So more and more charge can be given onto that system or arrangement of these two parallel plates, right? So what happened? This is the principle of what? Your capacitor. Let's see. Now it is based on the principle that when an ardent conductor is placed in the neighborhood of a charged conductor, the capacity of the system increases considerably. That means when you connect to the earth that uncharged body brought in the neighborhood of the charged conductor, then the capacity of the system increases. That is, the capacity, okay, increases when the potential difference is made reduced. That means your capacitance is what? Inversely proportional to potential. So if one decreases, if potential decreases, then what happens? Your capacitance will increase. That is saying here. So in figure A, let's see, potential decreases as induced negative charges try to reduce it, and hence capacity, okay, increases. That means what happened? This due to this negative charge, what happened? Potential decreases. And then what happened? If there is no positive charge, okay, on this side, then it would have been more what? Increase in its capacitance. Why? Because when we say potential, okay, if you try to bring this charge, when you try to send charge from here to here, due to these positive charges, these charges that is sent will be repelled. Suppose if you are going to send charge from this positive to this side, then positive charge need to be passed through it. Got it? Then what happened? Due to the negative charge, what happened? The positive charge will be attracted. But due to this positive charge, the charge that is sent from this side of the capacitor to this side, okay, this will act just like a capacitor. That's why I said as a capacitor. Got it? Due to these positive charges, the charge that is sent from this side of the plate to this side will be repelled. Okay, due to that repulsion, what happened? Positive charges what increases. But if it is going to be all negative charge, then it will be attracted, and if it is attracted, then more and more positive charge will be sent, and so what happened? The potential decreases, so capacitance increases. Got it? And there are two things to be understood here now about bound charges and free charges. Now these negative charges, okay, on to the uncharged body that is brought in the neighborhood of this charged body, what happened? These negative charges are called bound charges. Why? Because these negative charges, as long as positive charges, okay, are there in the neighborhood of this uncharged body, what happened? These negative charges will be there. These are bound. Okay, this cannot be moved. As long as this charged body is there, then these negative charges will be there. We call it this as bound charges. Okay, but these positive charges, they can move down freely, they can be removed. Okay, so these uncharged these positive charges that is set up on the further side of this conductor, okay, these positive charges are known as what? Free charges, because it can move freely down to the earth. Also it can be removed. That is the meaning. Okay, but as long as this positive charge is there in its neighborhood, these negative charges will be there. So we call it these as bound charges, and those positive charges which were residing on the further side of the uncharged body, they are known as free charges. Had there been this charged body been all negative charge, then this will develop opposite of that negative, means this will be positive charge and this will be all negative charge. So all those negative charges will be gone to the earth, and what happened? Whatever the charge that is here, that will be positive if this had been negative, I mean. Okay, so in that case, those positive charges develop here, that will be known as bound charges, and those positive negative charges that are developed on this side will be all gone down if this had been the negative charge. Got it? If this had been negative charge, then this would have been positive, and this will have been similar of that negative charge. Okay, so this will be positive and this will be negative. Okay, yes. So that is about free charges and bound charges. Got it? So let's see about the parallel plate capacitor. Right, so consider two parallel plates P and Q. Okay, P and Q separated by a distance small d. Okay, separated by a distance small b between this P and Q, and placed in vacuum. That means this is in vacuum. No medium is there in between the plates P and Q, such that this P, the plate P, is charged with plus Q. That means let this plate P be given a charge plus Q, plus small q, while the plate Q is added. Got it? So let's see again the diagram. So let this P and Q be the two parallel plates, okay, having common area capital A. Got it? And this plate P is given a charge plus Q, and this distance between the two parallel plate is having a distance small d, and they are placed in vacuum. So what happened when this P is given positive charge plus Q, then what happens? Similar opposite charge minus Q will be developed onto the nearer side of this charge conductor, and those similar charge, positive charge, okay, what develop onto the farther side of the plate Q will be all gone down to the earth. Okay, that is what it is happening in that parallel plate capacitor. So as there is no medium in between the two plate, we have to take it that this is the medium is what, vacuum or air. Now if sigma means this one is the surface charge density of the plate, then the electric field between the plate we have learned at the time of learning of electric field. Okay, electric field due to an infinitely thin sheet, okay, of infinite long or thin surface. Then what happened, this electric field due to that, we know that it is electric field is equal to sigma by twice epsilon naught if it is infinitely thin, right? So that sigma by twice epsilon naught will be given here along this line due to this positive charge, and due to this minus q charge on the other side, another electric field will be toward that plate Q. So Q, it will be equal to what, your electric field due to this negative charge will be what, sigma by twice epsilon naught, right? Let's see this sigma, okay, due to the positive charge it will be equal to what, due to the positive charge, okay, your electric field E, let's denote it by E plus, okay, due to this E positive charge, your electric field will be equal to what, sigma by twice epsilon naught, sigma by twice epsilon naught. Okay, let's erase it. Okay, sigma by twice epsilon naught, and it will be what, twice epsilon naught. Let me write like this. Okay, twice epsilon naught. So what happened, this sigma by twice epsilon naught, it is due to the positive charge. If it is for negative charge, that means due to this negative charge, sigma by twice epsilon naught will be again there. If it is for negative charge, say for negative charge also, it will be denoted by E minus, let's denote it by E minus, and for that E minus also sigma by twice epsilon naught will be there. But for this sigma by this twice epsilon naught, due to this negative charge, electric field will be also directing toward it, because this is negative, so electric field will be toward it. Okay, due to the positive charge, it will be emitting out from the plate P, and for this E minus, it will be attracting or toward the negative charge. Okay, Q, got it? Q means plate Q. So what happened, these two directions of the electric field, what happened, are along the same direction. So what happened, the total or net electric field will be adding that E plus and E minus. So as being the charge are of same charge density, sigma sigma, because same charge are there and common area is also there. So what happened, all will be the sigma will be same. Sigma will be Q by A, right? Q by A, Q is also here, minus Q is also here, area is also A. For this P also, area is also A, so sigma will be same, Q by A, Q by A. Okay, so Q by twice E, it will be coming, the total net field will be what, E will be equal to E plus of E minus, okay, due to the negative charge, so sigma by twice epsilon naught plus sigma by twice epsilon naught, that will give you what, sigma by epsilon naught. Okay, where epsilon naught is nothing but it is the permittivity of free space or vacuum, right? So the electric field between the two plate, okay, the electric field between the two plate is what, this from your definition of electric potential, we can define that electric potential is defined as the amount of work done per unit charge, right? So and then what happened from that definition of your potential gradient, electric field will be equal to minus of potential gradient, right? But if you take it only the direction, okay, only the magnitude, I mean neglecting the direction of that of the electric field and all, then what happen? If V is the potential difference between the plates, okay, if V is a potential difference between the plates, and then what happen if we take it that not take it that actually it is there, this electric field between the parallel plate, they are uniform, okay, they are uniform. If they are uniform, then we can take it that dV by dr as V by d only. Got it? So this electric field is equal to what? V by the distance d. So your V will be equal to ed. So you can remember this in that way, that potential is defined as the amount of work done in bringing a positive charge from infinity up to that point, okay. But here it is about the potential difference. If it is going to be the potential difference V between the two plates, then this will be the amount of work done in bringing a charge, a unit positive charge from one plate to the another plate, okay. That amount of work done, we call it that as what? Potential difference. So potential difference will be equal to force into distance. So you can remember in that way. So as I told you, in electricity, if you want if you hear the word potential, then you have to remember work done. If you remember this electric field, if you hear this word electric field, then you have to remember force. I said like that, no? So what happened? Potential will be equal to force into distance. So you can remember in that way also, okay. So what happened? Your E will be equal to sigma by epsilon naught into D, and sigma, we know that it is surface charge density. So total charge divided by total area, that will give you the surface charge density. Sigma by sigma will be equal to what? Q by epsilon, Q by A. Got it? So Q by A into D by epsilon naught, this will be the potential. So as if we have that potential, then we can easily find out the capacitance, which is equal to Q by A. So the total charge is what? Q, and what? V is what? Your Q D by epsilon naught A. So if you put these things, then in the capacitance, C is equal to Q by A, then we will get the capacitance of this parallel plate capacitor. Let's see. Now see, we have seen just now that B is equal to Q D epsilon naught A, right? So capacitance C will be equal to what? Q by V. So Q by V, B means what? Q D by epsilon naught in the denominator, right? So if you cancel Q, epsilon naught A will be in the numerator, D will be only there in the denominator. So your capacitance will be equal to what? C is equal to epsilon naught A by D, right? So this is the formula for capacitance when the intervening medium between the two parallel plate capacitor is either dry air or vacuum, okay. So now from this last resulting expression, we have seen that capacitance is directly proportional to what? Common area of the parallel plate. If area is large, then capacitance will be large. More and more charge can be stored if area is large. If the distance between the plate is decreasing, closer the distance between the two parallel plates, more charge can be stored, okay. So what happens? Its capacitance what? Increases, okay. If this distance decreases small, then this will be large, because they are inversely proportional. If this is small, this will be large. If this is large, then capacitance will be what? Small, okay. Now this is about the what? Intervening medium is air or vacuum. Had this intervening medium between the two parallel plate capacitor is replaced or inserted by some medium, okay, dielectric medium having dielectric constant K, then what happened? This epsilon naught will be replaced by epsilon naught K. That means what? If K is the dielectric constant of the medium between the two plates, then your C will be equal to epsilon naught K A divided by D, okay. Now see, in this case, what happen if dielectric medium is inserted in between the two parallel plates, then what happen? This a factor of K will be there. So what happen if dielectric constant K is replaced? If your vacuum is replaced by dielectric constant, then capacitance increases because K is always greater than 1. So what happen? Your capacitance increases when dielectric medium is introduced or is what inserted in between the two parallel plates, right? Now let's see about the what capacitance of a parallel plate capacitor when a dielectric medium or a slab is introduced or inserted in between the two plates P and Q, right? Why? Because in this, when dielectric slab or material is introduced, what happen? Polarization takes place. Got it? As polarization is taking place, what happen? The potential, okay, the electric potential or potential difference between the two plates decreases. Got it? So due to that, what happen? Capacitance will surely increase. Now let's see the step by steps how to find out the formula for capacitance for these parallel plate capacitors with a dielectric medium in between the plates. Okay, so consider two plates as we have taken in the previous case. Consider two plates P and Q having common area capital A and separated by a distance small d in between the two plates. Okay, and what happened in this case? Let's take it that before introducing this dielectric slab, okay, before introducing this dielectric slab in between the plates, let's take it that the capacitance that will be there in this parallel plate capacitor, let's take it that as C naught. Okay, C naught is for that capacitor having what vacuum, okay, in between the two plates. Its capacitance will be denoted by what? Epsilon naught A by D. So let's denote it by C naught, not for not having any medium or rather vacuum. Got it? So if E naught and V naught are the field and the potential difference between the plate, okay, in this case when there is no dielectric medium first, then what happen? E naught will be equal to sigma by that epsilon naught. This will be equal to what? Q by A epsilon naught, because sigma will be equal to total charge divided by total area, right? So it will be your epsilon naught will be equal to QA epsilon naught, okay, Q divided by A epsilon naught, I should say, and your B naught will be equal to what? E naught D, right? So then what happened in the next, let's see, when dielectric slab of thickness D is introduced, okay, when this dielectric slab is introduced, then what happened? The electric field which was there, E naught, this E naught reduces, okay, due to what? This E naught reduces because what happened? That E naught which was there in between the two parallel plates, due to the polarization, what happened? Polarization means what? Development of that opposite charges, okay. This one near the positive charge, it will be what? All negative charge will be developed onto the surface of this dielectric slab, and similar to that onto this, near to this negative plate, what happened? Opposite charge will be developed there onto the surface of the dielectric slab. So what happened? Electric field will be developed inside the dielectric medium. That means from positive charge to negative charge, it is denoted by EP, and the direction of the EP is from positive what of on its surface to the negative on its surface. Rather, this direction of EP will be against the direction of the electric field E naught, okay. So what happened? This E naught is acting from P to Q, whereas electric field due to polarization inside the dielectric medium will be acting opposite to it. That means from this side, P side, to Q side. Let me take it in that way, okay. So the net electric field inside the dielectric medium will be reduced. This is the net electric field or total electric field. Why? Because it will be E naught minus EP, as these two are in opposite direction. Okay, so what happened? Your electric field will be reduced. So that is what it is happening. But now you see that we cannot replace it directly, that E naught minus E naught is equal E is equal to E naught minus EP, because the thickness of this dielectric slab is not equal to D. Okay, let's take it that the thickness of the dielectric slab is denoted by T. So what happened? Your electric field in vacuum or in air is reduced by this T. Previously it was having the distance D for that E naught, but it has been reduced by a distance T, okay, of equal to the thickness of the dielectric slab. So as a result, the potential difference between the two plates changes from V naught to V. Now V decreases, such that what happened? V will be equal to what? E naught. This is the electric field in the space where there is no dielectric medium, and this is the electric field where there is dielectric medium. So E naught is the electric field where there is no dielectric medium, and E is the electric field where there is what? Dielectric medium. Got it? This E is equal to actually what? E naught minus what? EP. Got it? But we will not try to express in that way, rather we will try to express in terms of dielectric constant, right? So what happened? Your potential difference where there is no what? Dielectric medium will be equal to E naught times the distance where there is no dielectric medium, that means D minus T, and this is the portion of the electric potential difference due to that dielectric medium, or inside that dielectric medium having dielectric medium of thickness T. So E into T, where E is the electric field, net electric field in that dielectric medium. Got it? So this will be equal to what? E naught whole into D minus T, as it was there, plus this electric field, okay, in the dielectric medium, okay, in dielectric slab having thickness T, we can express this E in terms of that known quantity. We know that external electric field, we know the dielectric constant of that dielectric medium, so we can replace it E by E naught by K. Why? Your dielectric constant K is defined as what? Electric field in vacuum to that electric field in that medium, right? So this is the electric field in that dielectric medium, so E naught by E will be equal to K. So if you try to express this E in terms of this K, then what happened? E, capital E, will be equal to what? E naught by K. So let's replace it, this E by E naught by K. Got it? And then if you take it common from that relation E naught, then you will get in this way. V will be equal to what? E naught whole into D minus T plus T by K, right? Yes. So as we have the what expression of V, then we can easily find out for capacitance. Your capacitance will be equal to what? Q by V, right? So Q by V, we need to replace this V by the last expression that we have just found out. Then what happened? Your C will be equal to Q by V, which will be equal to also what? Q by epsilon naught D, epsilon naught into whole into D minus T plus T by K, that is here, right? Got it? And so what happened if you try to what? Take this epsilon naught as what? Epsilon naught means what? It will be sigma by epsilon naught, right? E naught, I mean sigma by epsilon naught. Sigma means Q by A, so Q by A divided by epsilon naught whole into D minus T by K. You just replace it, this E naught by that of Q, okay, by A into sigma into epsilon naught, because Q by A is nothing but that is sigma. So electric field in between the plate when the medium is vacuum or air, your electric field will be equal to what? Sigma by twice epsilon naught. Sigma is nothing but Q by A, right? So you just replace it, then you try to bring this upward. Q will be cancelled, then sigma epsilon naught times A will be there in the numerator, and what happened, this from the denominator, again whatever that remains in the denominator, you take it small d common, right? Then what happened, you will have 1 minus d by d plus d by dk. If you multiply this, then you will get d, right? If you multiply it with this and this, dd will cancel and you will have minus t. If you multiply it with a third term, then dd will cancel and it will be t by k, right? So you have to take common in this manner, right? Now what happened, if you bring this d in the numerator, then it will be epsilon naught a divided by d, and in the denominator it will be the what terms in the within the bracket will be there. Okay, so as it will be epsilon naught a by d, then that will be equal to what? The capacitance when there was no dielectric medium. Okay, that means in that previous slide you will find that E naught is equal to Q by A epsilon naught. Okay, so during that time the capacitance, okay, that is having before the introduction of this dielectric medium, let's take it that capacitance as what? C naught, which will be equal to epsilon naught A by D, right? So in that last expression, epsilon naught A by D will be replaced by what? C naught. Got it? And in the denominator it will be what is there in the what within the bracket, right? So if you replace it, then what happened, this last expression is nothing but this last expression is the what? Capacitance of that parallel plate capacitor. Okay, when dielectric medium of thickness T having dielectric constant K is introduced in between the plates, then this will be the last expression. And from here we found that the capacitance with dielectric medium is directly proportional to that of the capacitance when there is a vacuum alone. And we also know from it here that, let's see, when your this thickness of the glass slab is made equal to the distance between the plates, okay, that means when the whole of the space between the two parallel plate capacitor is completely filled with what? That dielectric medium. If the thickness of the dielectric medium is made equal to the distance between the plate, that means whole of the space between the two parallel plate is filled up with a dielectric medium. Then in that case what happened, this D is equal to D, so this D and D will be cancelled, T and D will be cancelled, so it will be having 1, and here it will be 1 by K, right? So that minus 1 and plus 1 will be cancelled, neutralize each other, and so 1 by K, if you try to bring that 1 by K, then it will come in the numerator, that K will come in the numerator. So your C will be equal to C naught by 1 by K, right? That 1 by K is not seen here. So what happened, that 1 by K, if you try to bring that K, if you try to simplify, then K will be coming here. So it will be equal to what? K times of C naught. Got it? Since what happened, your K is greater than 1, your K is greater than 1, what happened, your C is also greater than C naught. Got it? As this K will be always greater than 1, right? So as this K is always greater than 1, so what happened, your C, that means your capacitance of the parallel plate capacitor when what dielectric medium is introduced, what happened, it will be equal to K times, that means the dielectric constant times the capacitance of the parallel plate when there was no dielectric medium, that means in vacuum. Got it? That is what. So with the introduction of this dielectric medium in between the parallel plate, what capacitance enhance or increases. So it is what profitable to have some dielectric medium in between the two parallel plates. Capacitance enhance or increase means what? More charge can be stored. Okay, more charge stored means what? Electrical energy or electric field energy, you can say, or rather electrostatic field energy can be stored more when dielectric medium is placed in between the parallel plates. Okay, let's do it up to this only. In the next class we will do about that of the various type of grouping of capacitor or connection of capacitor like this. Okay, it may be in series or in parallel, so that one we will do in the next class. So for today let's wind up here. Okay, thank you.